but we actually skip around a little bit. The stuff we did in the last chapter was actually from chapter 13 and from other places. This one is mostly all out of chapter 12, but that's not a big deal. All we really use the books for, as you know, is homework, a little bit of homework out of that. All right. Now, think about what we did last three chapters. We talked about gases for 2. We talked about liquids, and we talked about solids. So those were last 3 chapters, solids, liquids, and gases. We even talked about the phase change between them, going from a solid to a liquid to a gas, and how it's the equilibrium, Le Chatelier's principle, all that stuff. Now we're going to mix them together. We're going to talk about mixtures. This chapter will not be all objective like the last one was. And the last one only had one problem on it, and it was on the back. This one will have quite a few problems and some chemistry reactions as well. So it's not going to be like the last one. But it's going to start out like the last one with quite a few notes. And because I have more notes, I have more demos. All right, so let's talk about different kinds of things that are mixtures and that we're familiar with, and things that are mixtures that we're not familiar with. We'll start with the easy ones of the types of mixtures, and those are the solutions. Solution's easy. We've seen solutions before. As a matter of fact, the definition I'm going to give you of solution is going to be the same one you got back when we were in chapter 1. When we were talking about elements, compounds, and mixtures. Same basic idea. We had a homogeneous, remember that homogeneous and heterogeneous back then? Same thing. A solution happens to be a homogeneous solution, or mixture, I should say, of 2 or more substances. And I hope you all remember what homogeneous means. What does it mean?
It's like all the same.
It's all the same. Same throughout. Uniform distribution of particles throughout. The same throughout. And you remember back in those, when I did those before, an example of a homogeneous solution probably was something like salt water or sugar water or whatever. And a heterogeneous solution was something like a chocolate chip cookie. Okay, because it's not the same throughout. So obviously a chocolate chip cookie is not an example of solution. A solution has to be homogeneous, which we're talking about these types. There are going to be 2 other types we're going to talk about in a minute. But a solution is going to be homogeneous, the same throughout, a uniform distribution of particles. Okay? And one other thing to keep in mind, for all of these guys we're talking about, they are not chemically combined. That's actually going to be very important. It may seem like a trivial thing now. Obviously, we're not talking about chemically combining them. But it actually becomes very important when we start to write equations for this, because yes, we are going to write equations, association equations, for when things dissolve. And they're going to look a lot like chemical equations, but they're not. And the way you're going to be able to tell that is going to be by looking at the state that they're in. Things that we've been ignoring up till now. You ever notice, I'm sure some of you have, I know some people have asked, there's a little S at the bottom of some elements, and a little AQ after others, a little L after others. And up till now, you say, well, just kind of ignore that for now. That's going to become very important. Because these are not chemical reactions. These are physical dissolving things. That's what we're talking about, not chemically reacting. All right, so that's what a solution is. Some examples would be stuff like, I have my examples in a minute. We'll talk about the different parts of the solution first. 2 parts of a solution, I bet you can tell me. What are the 2 parts that make up a solution? In any solution, you have more of one thing and less of another. What do you call the thing you have more and less of?
Products.
No, then that's a bad answer for a couple reasons. You don't have a product. The product's implying I have a chemical reaction. Okay? I don't have a chemical reaction going on. I just said that. No. The 2 parts of this. If I mix salt in water, what do I call the salt? They both begin with S.
Solvent.
Well, which one do you think is a solvent? And what's the other word? Solute. Right. You have solute and solvent. Which one's which? If I had salt dissolved in water.
Solvent's the water.
Solvent's the water. The solute's the... the salt's the solute. How do you know? What's the difference?
One dissolves the other.
One dissolves the other. What if I had 2 gases? Then they have no. What do you think? There you go. That's it. The solute's the guy you have less of. The solvent's the guy you got more of. There you go. Good. So that's why if I put a tablespoon of sugar in water, the solvent would be the water, and the solute would be the sugar. Because you do have to keep that in mind. You actually can have a lot of different types of solutions. You don't just have to have, I use salt and sugar water as my most obvious ones because you guys are used to seeing those. You've all drank, Kool-Aid and iced tea and lemonade, and all of them are just sugar and water. And you all swam in the ocean where it's salt water. Okay, those kind of things you're familiar with. But I can have a lot of different solutions, a lot of different types of solutions. Okay, not just the obvious ones, but air is a solution. You don't think of it, but it is. So in air, you have a gas like oxygen dissolved in another gas, nitrogen. And there's other trace gases in there as well. In the case of salt water, your salt's your solute, water's a solvent. Can you think of a case where you could have a liquid? So here, a salt water would be a solid dissolved in a liquid. Can you think of a place where you could have a liquid dissolved in a gas? A liquid dissolved in a gas. Humidity.
Water vapor.
Yeah, water vapor, sure. Water, humidity in the air, water vapor. That's the water, still liquid dissolved in air. Okay, can you have a solid dissolved in a solid? No, you can't do that. Sure you can. All right, we call those alloys, and basically most of you have one on. Some things that's made of metal. It's rare it's a pure metal. It's not pure iron. It's not pure gold, even if it's an earring. It's usually gold mixed with something else. All right, and but it's a solution. It's actually a solution, even though it's a solid. So you can have all kinds of solutions. On page 377, you'll see, and I have that same chart from the book up here in a second. There are a lot of different solutions that you could possibly have, possibilities. Like, for example, your gas in a gas, air, nitrogen and oxygen. Gas in a liquid, soda. Liquid in a liquid, vinegar. Or alcohol, beer, right? Solid dissolved in a liquid. Obviously, those are the most common ones. We have almost all the chemicals used back there. If they're in solution, that's what it is. Liquid in a solid. Solid in a solid. Okay, there's a lot of possibilities there and more. And by the way, I said about gold. If you have a gold earring on, if you have a gold ring, chances are it ain't 24 karat pure gold. It's probably something less than that. The reason being, 24 karat pure gold is going to be pretty soft. Gold itself is pretty soft. You really make something out of gold, and it never will tarnish. That's true. But I know for a fact, even my wedding ring, if I don't take it off, I don't ever take it off. So basically, but when I do look at it, it's not even a circle anymore because it's like just all misshapen. And you may notice that even with earrings and stuff like that. So you add a little bit of silver in there, and it makes it, or copper, and it makes it a little bit harder, but it still looks like gold. It has most of the properties of gold. All right. So those are solutions. Those are the easy ones. I didn't do a demo for that. I have some demos that are going to be for the things that are not so easy. I think most of us know solutions. We don't know what a suspension is. Suspension is what you're going to get if you get into a fight in the hallway. 5 days, I think it is. But that's not the kind of suspension I'm talking about.
Yeah.
Why? Who's been in a fight? Josh?
No, not me.
Not you.
It was me.
I punched a girl in the face.
Excellent. Emily.
Ben.
Good job.
Ben. You want to relive?
Ben, have you been fighting again?
Not lately.
Not lately? Good. All right. I don't know who's been in a fight. I have no idea. They're just
That was
making
like his career. Cool.
great school. Really?
Yeah, like really like elementary.
I think Josh
That's
is.
what you did. You beat people up.
That's what he did. He was the enforcer. All right. Anyway, I don't know.
Oh my God.
Either way. Either way.
On the playground, beat the crap out of
What is a suspension? A suspension is not a homogeneous mixture. It's a heterogeneous mixture. It means it's not exactly the same throughout. And I can show you a couple of examples of suspensions. And I'm going to show you a couple of examples of suspensions with demonstrations. I'm going to demonstrate for you first off back there, but it's going to take me about 10 or 15 minutes to let it run. Milk. How milk is actually technically a suspension. The milk that you drink, all right, the milk that comes out of a cow. If you were to let it sit, it would just settle out into two layers, a layer of cream on the top and a low-fat milk on the bottom. That's what used to happen before it was homogenized and pasteurized, before it goes through that process. So I'm going to do a little demo with that. I'm going to come back and do a little demo with this, but it takes me a little while back there, so I'm going to stop. Why would they be lying? They're not lying. Look at it. The milk I have back there, right now I'm separating. I'm separating it out by using the fact that the water that's part of the milk is heavier than the cream. Cream. Ever hear the phrase "the cream rises to the top"?
No.
Well, it's a phrase. Anyway, it doesn't really matter. If you were to get whole milk that was not pasteurized and not homogenized, I should say, you would find that just letting it sit in a bottle, you'd have the top layer would be cream and the bottom would be a low-fat milk. All right. Now, I'm going to show you that in a little bit. We'll come back to that, but let me show you another example of a suspension in a second after I finish the notes on it. All right. The solute particles in a suspension are large. They're very large. They're so large they can't stay suspended. It's kind of weird. I call it a suspension, but really it's not. It doesn't stay suspended. That's the whole point of a suspension. It actually goes back. It settles out. It settles out upon standing because the particles are so large. Some examples of that would be, well, can you give me, before I put them up there, can you give me some examples of things that settle out, that separate, whether they're foods, drinks? Give me something that separates besides milk, which you wouldn't have guessed because milk really doesn't separate your refrigerator. What does separate your refrigerator? A couple of things. Italian salad dressing, absolutely. That's going to be one of my examples up here, and I'm going to do it for you over here. Oil and vinegar don't mix. Oil and water don't mix. What else? You have 2 layers then. We have to shake before you use it. How about paint? You ever open a can of paint?
Oh, yeah.
It's all clear liquid on the top, and then the color stuff is on the bottom. Okay? You're not going to eat the paint, drink the paint. Well, still an example of a suspension. All right. Some other examples here. Milk, like I said, doing back there. Muddy water, oil and vinegar, salad dressing. Paints. Some people always say fresh squeezed orange juice. That would be another good example. Fresh squeezed orange juice would have the pulp. Usually, if you look at the store that has clear bottles of that stuff, when it has pulp in it, pulp usually settles to the bottom. It's clear on the top. There's a lot of things that you used as a kid that were suspensions. A lot of medicines. Remember that pink stuff that always you had to take when you were a kid, the amoxicillin, right? Tasted like, not the cough medicine now, the antibiotic. Tasted like bubble gum maybe or strawberries. And that stuff, you had to shake it up. It says right on it, oral suspension, which means you're going to drink it, but you should shake it up first, all right? Because if you don't, you're not going to be getting it, all of the stuff mixed together. Another example, you guys probably had poison ivy maybe or chicken pox, and you had to put calamine lotion on there. You ever had that? What calamine lotion looks like? That pink. It also is pink. Okay. Well, I remember one time when my kids had chicken pox, pouring out some calamine lotion without shaking it up, and it poured out completely clear. Clear. You say, what is pink? Yeah, but if you don't shake it up, the clear layer on the top, the watery layer is on the top, and all the pinks on the bottom. So it poured out completely clear. A lot of things are like that. If it says suspension on it, or if it says shake well before using, it's probably a suspension. Right? You have to shake it up first. Let me show you one before I go on here. Another suspension here I'm going to make, and it's one that you've all seen before, I'm sure. If I take some water, okay, it's plain old water, and I add some oil to it. I'm doing this for a reason because I'm going to eventually, after this, do something else to it to make it something other than a suspension. If I add some oil to my water, I think you all agree it's not going to mix. Just stays on the top there. Can you all see that? 2 layers. The oil on top and the water on the bottom. Okay. I can shake it up. And if I shake it up like I do with my salad dressing, for example, it'll stay suspended for a very short time. Okay? But very quickly, it will start separating back out. And we'll look at that in a few seconds, and I'll show you how it does. All right? But I can do something to it. What kind of salad dressings? There are other kind of salad dressings you have that you use. Ranch, right? Thousand Island, French. Those kind of salad dressings, you don't shake up as much. You don't really have to. When you look at it in the refrigerator, you don't see 2 layers. This one's already separated back out. Look, there's a layer of oil on the top and the water on the bottom. See it? Okay, oil on the top, water on the bottom. Well, watch what happens. I'm going to go to the third thing, that type of mixture that's like a solution but not. And I'm going to add a little bit of soap to this guy. If I add some soap, then I do exactly what I did a minute ago. I shake it up. Okay? And I look at it again. This time, when I look at it, you'll notice, although there are some, we'll put that light on the front here. You can see better probably. There are some bubbles in the top. Okay? But for the most part, if you look at this guy, he is not going to separate out very quickly. He's going to stay together. The other one separated out in a matter of seconds. All right? I'll come back to, I'll show you that again in a little bit. He will still be like that. So basically, you can turn it off again. If you want to keep your oil and vinegar salad dressing from separating out, just add a little soap to it.
Okay.
No, not soap. What I don't want to add soap to it because I don't want to throw up. I don't want to add soap to it because it doesn't taste good, right? What could I add to it that is edible but will keep them from mixing, keep them from separating out? Nope.
You don't do anything, you just shake it up before you eat it.
Yeah, why don't they do that?
Well, they do. That's why it's exactly what they do. That's why you have the different. How do they make ranch, French? What's the base for that? Is it oil and vinegar? In effect, it is. In effect, it is because what do you think they're using in ranch or in Thousand Island?
A creamier thing?
What's the? It's not cream though. What is it? They use to keep the stuff. It doesn't separate out. Not butter. We're gonna get it. Begins with an M.
No.
Not milk.
Marmalade.
Marmalade. It begins with an M. It ends with A and A's. Yes. Yes. Now, let me explain. Does anybody know what mayonnaise is? Mayonnaise is just oil and vinegar. It is just oil and vinegar. The difference is you've also added some egg whites, whipped it together, and the egg whites act as an emulsifier, keep it from separating back out. So that's why, basically, you can have creamy Italian dressing. It's basically, instead of using oil and vinegar alone, you're using mayonnaise, which is oil and vinegar. It's just that it's got egg whites in it to keep it from separating out. All right, so this guy is not separating out. I didn't use egg whites. I use soap. But if I wanted to be able to eat it, I would use something that I could use as an emulsifier, like egg whites. There's other things you can use. If you look at your candy bars, a lot of them are held together by other kinds of emulsifiers like guar gum and lecithin, different chemicals that you could use that will keep things from separating. All right, but they are same basic idea. Now that is an example of. This is an example of. Mayonnaise is an example of. The next guy, which is, you don't need that out, which is a colloid. Now a colloid is kind of in between both. It's not a solution. It's not perfectly homogeneous. The particles are a little bit larger than a solution. However, they're not so large that they actually settle out. It's a heterogeneous mixture which does not settle out and can't be filtered either. Now, I have a good example of that. Besides the one I just made there with the soap and the oil and the water, I can make another one. I'm going to show you another one. They look very similar. You don't have to tell them apart. I'll bet you can. Well, maybe you can. I will. So basically, the heterogeneous mixture here for a colloid, the particles are in between. They're in between the size of a solution whose very small particles and stay suspended, and a suspension whose particles are so large they actually settle out. Okay. Now, I'm going to show you something about these guys. I'm going to illustrate it with this. You turn those lights on again? Illustrate with these two yellow, certainly look like yellow solutions. If you look at this guy and you look at that guy, you would certainly say they both look homogeneous. No real difference here. You don't see layer here and a layer down there. Okay? Certainly look like solutions. But believe it or not, one of them's not. Both of them both of them contain food coloring. Okay? Both of them contain sugar. But one of them also contains jello. And I want to show you, it's maybe hard to tell from where you are right now which one's which. And by the way, it's not Jell-O that got hard, so obviously both of them are moving around. I didn't heat it up and let it cool down. I just added the Jell-O and then I filtered it. And so they look awfully clear, but I'm going to use a laser to show you that they're not. This is my pocket laser, very portable.
Awesome.
Yeah.
The right one is clear. Josh.
Turn that light off, both of the lights off for now. Okay. This is my pocket laser. If you look back there, you can see. Take a look back in the room. It's actually a little bit more powerful than the laser you would have from. Well, now don't have to do it without hitting your eyes. I wonder what it would look like if I put up the camera. Watch this. It's gonna be like Captain Picard here. Look at that. That's cool. Wow, that's really cool. You guys have to. Oh, I'm probably ruining the lens, by the way. Last thing I'm ever making. Last video. So I feel like I'm a Borg. You guys ever watch Star Trek? No. Captain Picard got. No, I guess not. All right, check this out. The particles may not be large enough to see with the naked eye, but they're large enough to see with a closed eye. Not just kidding. With a laser. Take a look at the laser. All right. I can see, and if you can't, get to yourself, stand up and get to your place where you can look through here, and I can actually see the beam through this guy here, but I can't really see the beam through this one. Okay, if you want to come up here, you can see it a little bit better even. Gather around if you want to, without knocking over Zach's stuff. Marvin. Look down from the top, and you'll be able to see it very obvious. See the beam from the top? Well, after you look, go and have a seat again. Have a seat after. Don't move the camera either. Don't touch the camera. Okay. See it? Okay. After you've seen it, let other people get it. If you look, you see the beam goes right through it. That's called the Tyndall effect. We're going to get that in a minute in the notes. Don't hit my camera.
Oh, that's weird.
Y'all see it? Okay, hit that backlight on for me and see if my camera's ruined. No, not yet. All right. So that's called the Tyndall effect. And it turns out that those particles may not be big enough to see, but they're large enough to scatter light. Okay? Take a look. Write that down. Emily, wake up.
I'm bulking up.
You're bulking up?
We're very hostile to you lately, yeah.
Yes, I have a tendency to do that when people sleep in my class.
I'm not sleeping. I was resting my eyes.
You're inspecting the
But
inside
I
of your
seriously
eyelids.
was, though. That's the thing. I wasn't sleeping. I was seriously just resting my eyes. I was blinking. I took a long blink.
It was a very long blink. All right. So some examples of this would be, I already mentioned a few of them. Jell-O, the one I have up here. Mayonnaise, I talked about before. Milk technically is too, because it's been homogenized. But that'd be a tough one. I wouldn't put that one down. But certainly fog, any kind of gel or foam. So like toothpaste, hair mousse, not the kind with antlers. Any kind of a foam or a gel that does not settle out. Whipped cream, Cool Whip, right? Cool Whip? Okay. Mayonnaise. I want to show you that while the camera's still on too, but copy this homework down really fast. That's not much. You'll be doing that while I'm giving you your test grades, which will be in a few minutes. But I also want to show you that back there as well. Copy that homework down.
Whoa.
It's also up here, if you don't see it there, and you can enjoy. What's that an example of?
Trees. Trees.
Turn the light up.
Nature.
Definitely trees.
What is an example of?
Trees.
A greenhouse.
Sunlight.
What's an example of?
Dust.
Fog.
Trees. Dust.
What's an example of?
Grass. Dust.
Wow.
Dust. Dust in the air.
Some buildings in the background of the picture.
Give you $1 million if you tell me that's an example of. The Tyndall effect. Yay!
Sunlight.
Get $1 million.
Put that light back on now.
I seriously don't get it.
Look here.
That's.
I said a cowboy.
Okay, now I'm going to bring this one up here.
I'm mad. Honestly, it's been going like this.
You can see. I know you can't see really well, but I have to show it to the camera first, and then I'll show you guys closer up too. Right. if you look at this guy, turn the light on again. The very top of this, I've got a white layer. And that white layer here versus the blue down here, that's the cream. You can leave the light on. That's the cream that's on the top, and the liquid. And notice the reason I put blue food coloring is very simple. It's going to actually lead us into tomorrow's class, which is about the solutions and how things dissolve. Turns out that blue food coloring dissolves very well in water, but not so well in cream or in fat. So it's very white at the top here, and the blue food coloring is down in the watery layer. Okay, and you can see there's two layers. So even though it's been homogenized, I was able to separate it out at least a little bit. Not great. If I had, like I said, fresh milk from a cow, it would separate out a lot better and a lot faster. All right. Okay, let me shut this off.